Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the series solution of ordinary differential equation. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. So before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the two-dimensional Laplace equations. In the fourth module of mathematics 3, that means partial differential equation and series solution of ordinary differential equation. So in this lecture we have discussed about the Laplace equation in two dimensions, and after that we have talked about the solutions of Laplace equations. So, the equation is of the form del 2u del x square plus del 2u del y square is equal to 0. Okay, this is the Laplace equation where u is a function of x comma y. After that we have talked about some related examples on the Laplace equations. Okay, so today we are going to discuss about the series solution of ordinary differential equation, and this is my fourth lecture on partial differential equation and the series solution of ordinary differential equation. So here is the content of today's lecture. So in this lecture, we first of all we will introduce the Taylor series solutions of the function at any point. Then we will discuss about the validity of series solutions, okay, of ordinary differential equations. And after that, we will discuss about the general method to solve the ordinary differential equation, and then we will study on the Frobenius method to solve the ordinary differential equation. Okay, so there are two methods for solving the ordinary differential equation. First method is the general method, and the second method it is Frobenius method. Okay, so we will discuss in lecture 4. So let us begin with the introduction of the series solution of a ordinary differential equation. So sometimes we face some differential equation which cannot be solved by the method discussed so far. So far we have discussed the solution of a ordinary differential equation, and we have already discussed how to solve the ordinary differential equation by using the d operator method or variation of parameter methods, okay, and so on. And applying the Laplace equation, we have already solved the differential equation. So but sometimes we cannot solve the differential equations. Okay, so such type of equations may be solved by assuming that an infinite convergent series arranged according to the ascending power of the independent variables satisfied the equation approximately. According to that, we will define the power series of a function. So a power series is the sum of the infinite number of terms of the functions, and it is equals to s, and s is equal to a0 plus a1 into x minus x0 plus a2 into x minus x0 whole square plus a3 into x minus x0 whole to the power 3 and up to infinity. That is the Taylor series expansion, the power series about the point x is equal to x0. And it can be written as a compact form, summation m is equal to 0 to infinity m into x minus x0 whole to the power m. Okay, so where a0, a1, a2 up to infinity are constant, called the coefficient of the series, and that means the Taylor series, and x0 is also a constant and it is called a center of the series. Okay, so a power series does not include terms with negative powers. So here the powers of the series are all positive terms, not negative terms. Okay, so a power series, that means a Taylor series, does not include terms with negative power. It is always positive power. So therefore the linear differential equation with constant coefficient always process series solutions. Okay, so we can solve the differential equation by using the series solutions. So therefore, the homogeneous solution of the linear differential equation with constant coefficient. So this is the second order linear differential equation, y double dash plus a into y dash plus b into y is equal to rx. Okay. So here a and b are the constant, and r is a function of x or constant. We'll have one of the type of the solutions. So any second order differential equation, there are three possibilities. So you know, any second order differential equation, the solutions is depend on the nature of the roots. Okay, that means where the auxiliary equation is say m square plus a into m plus b is equal to 0. Okay, where rx is equal to 0. So the solutions of this differential equation where Rx is equal to 0 and t is equals to either C1 into e to the power lambda 1x plus C2 into e to the power lambda 2x. And in that case where lambda 1 and lambda 2 be two roots, and these two roots are real and distinct. Or y is equal to a plus bx into e to the power lambda x, in that case where the roots are real and equal. Okay, or y is equal to a cos alpha x plus b into sin alpha x into e to the power beta x. So in that case where the roots are imaginary, and here m is equal to alpha plus minus I into beta. Okay, so the solutions of this second order differential equation is either c1 into e to the power lambda 1x plus c2 into e to the power lambda 2x, or y is equal to a plus bx into e to the power lambda x, and y is equal to a cos alpha plus b sin alpha into e to the power beta x. And these three solutions are depend on the nature of the roots of auxiliary equations. Okay, so all of these solutions can be expanded in power series of x. So for example, say e to the power x. So e to the power x is a transcendental function, you know, and the power series of e to the power x, it is equals to 1 plus x square by 2 factorial plus x to the power 3 by 3 factorial. Okay, and up to infinity. By applying the Taylor series expansion, we will get this one. And the compact form of this series is equal to summation of our m is equal to 0 to infinity x to the power m by m factorial. Okay, so this is the series solutions of the function e to the power x. Similarly, we will find the series solution of the sine functions sin x. Okay, so the Taylor series expansion of the sin x, it will be x minus x to the power 3 by 3 factorial plus x to the power 5 by 5 factorial. Okay, and up to infinity, minus x to the power 7 by 7 factorial. Okay, and up to infinity. And the compact form of the sine series, it will be summation over m is equal to 0 to infinity minus 1 whole to the power m x to the power 2m plus 1 by 2m plus 1 factorial. So this is the compact form of the series sine x. Okay, so the series power form of y can be accepted as a solution provided that the differential equation is satisfied by it and the series is convergent. So in both cases the series are convergent series. Okay, these are the compact form of the series e to the power x and sin x. Let us move on the next slide. So in this slide we will discuss about the validity of series solutions. Okay, so consider a second order linear differential equation of the form. So this is the second order linear differential equation. Okay, homogeneous, where the right side is 0. So p0x into d2y dx2 plus p1x dy dx plus p2 of x into y is equal to 0, and we can write it equation number 1. So where p0, p1 and p2 are the polynomial function of x. Okay, so where p0 and p1 and p2 are the polynomial functions in x. Okay, so as every differential equation of the form 1 may not have series solutions. Okay, so we now find the conditions under which the above equation has series solutions. So every second order differential equation cannot have a series solution. So in that case, if p0 of a is not equals to 0, then the point x is equal to a is called an ordinary point. Okay, So while p0 of x is a polynomial function or the coefficient of d2 I dx2, and if at the point x is equal to a, p0 of a is not equals to 0, then x is equal to a is called the ordinary point, where a is any arbitrary point. Okay. Otherwise, x is equal to a is called a singular point of equation 1. So hence, equation 1 can be written as, so after divided by p0 of x on both sides, we will get d2y dx2 plus p of x dy dx plus q of x into y is equal to 0, and we can write it equation number 2. So where p of x is equal to p1x by p0x and q of x is equal to p2x by p0x. Okay, after divided by p0x on both, we will get this one. So therefore, if x minus a into p of x and x minus a whole square into q of x possess derivatives of all order in the neighborhood of x is equal to a, then x is equal to a is called a regular singular point. Okay. So in that case, where px is equal to p1x by p0x and q of x is equal to p2x by p0x. Okay. So these two terms possess derivative of all order in the neighborhood of x is equal to a. Then x is equal to a is called a regular singular point. Here is the example of the regular singular points or the validity of series solutions. So consider the equation x minus 1 into d2y dx2 plus x into dy dx plus 1 by x into y is equal to 0. Okay, this is the second order differential equation, and which can also be written as x into, after multiplied by x on both, we will get x into x minus 1 d2y dx2 plus x square into dy dx plus y is equal to 0. So in that case, where p0 of x is equal to x into x minus 1 and p0 of 0, so at x is equal to 0, p0 of 0 is equal to 0, as well as at x is equal to 1, p0 of 1 is equal to 0. So x is equal to 0, 1 are the singular point of the given differential equations. Here also p of x is equal to p1x by p0x. So and you know where p1x is equal to x square and p0 of x is equal to x into x minus 1. So after simplifying it, it will be x into x minus 1 and qx is equal to p2x by p0x, and it will be 1 by x into x minus 1. So therefore, x into p of x is equal to, x square by x minus 1, and x square into q of x is equal to x by x minus 1. So since x into p of x and x square into q of x possess derivative of all orders in a neighborhood of x is equal to 0. So in a neighborhood of x is equal to 0, the first derivative, second derivative, and up to infinity, that means third, fourth, okay, and all the derivatives in a neighborhood of x is equal to 0 are exist. So x is equal to 0 is a regular singular point of the given differential equations. Okay, and I have already mentioned in the previous slide. I have already defined in the previous slide how to find the regular singular points of a differential equations. Okay, so in that case, x is equal to 0 is the regular singular point, as well as x is equal to 1 is also a regular singular point of the given functions. X into x minus 1 into d2y dx2 plus x square into dy dx plus y is equal to 0. Okay. So after that, we will discuss some theorem on series solutions. So here is the theorem. The first theorem, it will be when x is equal to a is an ordinary point of equation 1. That means p0 of x d2y dx2 plus p1x dy dx plus p2 of x into y is equal to 0. Then its solution can be expressed as a series of the form y is equal to a0 plus a1 into x minus a plus a2 into x minus a whole square and up to infinity. This is the Taylor series expansion when x is equal to is an ordinary point. Okay, so the compact form of this series is equal to summation over n is equal to 0 to infinity n into x minus a whole to the power n. That is the differential equation has a series solution when x is equal to is the ordinary point of the given differential equation. And the theorem 2, it will be when x is equal to a is a regular singular point, okay, of equation 1. That means p0 of x plus p1 of x into d2y dx2 plus p2 of x into y is equal to 0. Then its solution can be expressed as a series of the form y is equal to x to the power n into a0 plus a1 into x minus a plus a2 into x minus a whole square and up to infinity. And it is equals to summation over n is equal to 0 to infinity n into x minus a whole to the power n plus a. But m may be positive or negative integer or a fractions. That is, the differential equation also has a series solutions. Okay, so there are two theorem on the series solution, and the first theorem, it will be when x is equal to a is the ordinary point on the given differential equation. Then the solution can be expressed as a series of the form y is equal to summation over n is equal to 0 to infinity n into x minus a whole to the power n. And when x is equal to is a regular singular point, then the solution can be expressed as a series solution of the form y is equal to summation n is equal to 0 to infinity n into x minus a whole to the power n plus n, where m may be positive, negative, or the fractional number. This type of solution is called the Frobenius solutions, and the first one, and this is called the general solution of the given differential equation, and this one is the Frobenius solutions of the given differential equations. Okay, so let us move on the next slide. So in this slide we will discuss the general method to solve an ordinary differential equations. Okay. So here we discuss two methods depending on the nature of the points x is equal to x0, about which the series solution is convergent. So in that case we will discuss the two methods for which the series solution is occurred. So the first method is the general method for solving the differential equation when x is equal to x0 is the ordinary point. And the second method, it will be Frobenius method when x is equal to x0 is the regular singular point, okay, of the series solutions. So the first method, it will be the series solutions of the power series solution when x is equal to x0 is the ordinary point. So in that case we will take a solution can be expressed as y is equal to summation n is equal to 0 to infinity n into x minus a whole to the power n. Okay, be the series solution of the ordinary differential equation p0 of x into d2y dx2 plus p1x dy dx plus p2 of y is equal to 0, and we can write it equation number 1. So you know this is the series solution of the given differential equation. Then from this we'll get dy dx is equal to, okay, after differentiation we'll get dy dx is equal to summation over n is equal to 1 to infinity n into n x minus a whole to the power n minus 1. And the second order differentiation of the given series solution, it will be summation n is equal to 2 to infinity n into n minus 1, where n be a finite number, and it will be n into n minus 1 n into x minus a whole to the power n minus 2. Okay, so now substituting these values in equation 1, that means d2y dx is equal to this and dy dx is equal to this and y is equal to this. Okay, so then equating the coefficient of x to the power n to 0, and we get the relation between an and an plus 2. Okay, so after substituting these three differentiation, that means d2y dx to dy dx and y, in equation 1 we will get the coefficient of x to the power n, and if the coefficient of x to the power n it will be 0, then from this we will get a relation between an and an plus 2, and which is called the recurrence relation. Okay, and from this relation we will obtain the coefficient of 1 in terms of a0 and a1, and these are the substituted in 1 to get the required solutions. Okay, so from this differential equation we get the solutions, and this solution is in the terms of a0 and a1. Now we will solve some related examples by applying these methods. So here is the example. Find the power series solution of the equation x square plus 1 into y double dash plus x into y dash minus x into y is equal to 0 in power of x. That means about the point x is equal to 0. Okay. So here is the given differential equation x square plus 1 y double dash, that means d2y dx2. Okay, and it can be written as y double dash also, plus x into y dash, that means x into dy dx minus x into y is equal to 0, and we can write it equation number 1. So now comparing this equation with p0x y double dash plus p1x y dash plus p2x y is equal to 0. So where p0 of x is equal to x square plus 1, okay, and p1x is equal to x and p2x is equal to minus x. So p0x, p1x and p2x are the polynomial function in x or constant. So in that case, where p0 of x is equal to x square plus 1. Okay. So here p0 of 0. So we are going to find the power series expansion or power series solutions about the point x is equal to 0. So at x is equal to 0, that means p0 of 0 is equal to 1 and it is not equals to 0. So x is equal to 0 is an ordinary point of equation 1. That means the given equations. Okay. So we take a power series y is equal to a0 plus a1x plus a2x square, that means summation over n is equal to 0 to infinity n into x to the power n. This is the power series we will take when x is equal to 0 is the ordinary point, and we can write it equation number 2. So therefore the derivative of equation 2, it will be summation n is equal to 1 to infinity n into an x to the power n minus 1, or n be any finite number, and as well y double dash is equal to summation n is equal to 2 to infinity n into n minus 1 into an x to the power n minus 2. Okay. So now substituting the above values of y, y dash and y double dash in equation 1, that means this equation, so we get x square plus 1 into y double dash, that means summation over n is equal to 2 to infinity n into n minus 1 n x to the power n minus 2 plus x into y dash, where y dash is equal to this, that means summation over n is equal to 1 to infinity n into n x to the power n minus 1 minus x into y, where y is equal to summation over n is equal to 0 to infinity n into x to the power n is equal to 0. Okay, so therefore from this we will get summation n is equal to 2 to infinity n into n minus 1 n x to the power n plus summation over n is equal to 2 to infinity n into n minus 1 n x to the power n minus 2 plus summation n is equal to 1 to infinity n into n x to the power n minus summation n is equal to 0 to infinity n into x to the power n minus 1 is equal to 0. Okay. So in this equation, where the first term will be divided into two parts. Okay. So first part is this and second part is this. So therefore this equation will reduce to summation n is equal to 2 to infinity n into n minus 1 n x to the power n. Okay. So the first term will remain same, the second term will be changed. So in that case, where n minus 2 is equal to n, so n is equal to 0 to infinity and n is replaced to n plus 2, n minus 1 is replaced to n plus 1, okay, and n is replaced to n plus 2 and n minus 2 is replaced to n, plus summation n is equal to 1 to infinity n x to the power n. So the third term will remain same, and in the fourth term here n minus 1 is equal to n square. Okay, so that is summation n is equal to 1 to infinity n minus 1 x to the power n is equal to 0. So after simplifying this equation, above equation, we will get summation n is equal to 2 to infinity n into n minus 1 n x to the power n. So this term, first term will remain same, plus 2 into a2 plus 6 into a3 into x. When we put n is equal to 0 in the second term of the above equation, that means this equation, we will get 2 into a2 and when we put n is equal to 1, we will get 6 into a3x plus summation of n is equal to 2 to infinity n plus 2 into n plus 1 into a n plus 2 into x to the power n. Okay, plus summation n is equal to 1 to infinity n into n x to the power n minus summation n is equal to 1 to infinity a n minus 1 into x to the power n is equal to 0. That means the third and fourth term are remain same. And the above equation implies summation n is equal to 0 2 to infinity n into n minus 1 a n x to the power n plus 2a2 plus 6a3 into x plus summation n is equal to 2 to infinity n plus 2 into n plus 1 a n plus 2 x to the power n plus a1 plus x, and in that term when we put n is equal to 1 we will get a1 into x plus summation n is equal to 2 to infinity n into n x to the power n minus in the last term when we put n is equal to 1 we will get this one a0x, okay, minus summation n is equal to 2 to infinity a n minus 1 x to the power n is equal to 0. So therefore this equation will reduce to 2 into a2 plus 6 into a3 plus a1 minus a0 into x plus summation over this, okay, and we can write it equation number 3. So since equation 3 is an identity, so equating the constant term of the coefficient of the variance power of x to 0, we'll get, first we will take 2a2 is equal to 0, so that means a2 is equal to 0. And in the second coefficient, that means 6a3 plus a1 minus a0 is equal to 0, okay, and the third coefficient will be this is equal to 0. So therefore the coefficient of x, that means x to the power 0, x to the power 1 and x to the power n are equals to 0. That means 2a2 is equal to 0, from this we will get a2 is equal to 0, 6a3 plus a1 minus a0 is equal to 0, and from this we will get a3 is equal to a0 minus a1 by 6, and from the third, that means the coefficient of x to the power n, and it will be n into n minus 1 n plus n plus 2 into n plus 1 a n plus 2 plus n into n minus a n minus 1 is equal to 0 for all n greater or equals to 2. Okay, from equation 3 we will get this one. This is the third coefficient, that means x to the power n of the previous equation. So from this we will get the coefficient, that means a n plus 2, and it will be a n minus 1 minus n square into n by a n plus 2 into n plus 1. After simplifying this equation we will get this one for all n greater equals to 2, and we can write it equation number 4. So the above equation, that means the above relation 4 is known as the recurrence relation of the given differential equations. So now we put n is equal to 2 in equation 4, we will get a4 is equal to a1 minus 4a2 by 12, and here a2 is equal to 0, so from this we will get a1 by 12. Okay, and if we put n is equal to 3 in that equation, we will get a5, and a5 is equal to a2 minus 9a3 by 20. Okay, and but you know a3 is equal to a0 minus a1 by 6, so and a2 is equal to 0, you know, so from this we will get minus 9a3 by 20, and a3 is equal to this, that is minus 9 by 20 into a0 minus a1. Okay, so after simplifying we will get minus 3 by 40. So if we put a3 is equal to this, we will get minus 3 by 40 into a0 minus a1. Okay, and this is the value of a5. So therefore now putting the value of a2, a3, a4, a5, etc. in equation 2, and equation 2 is the required series solutions of the given differential equations. Okay, so if we put a3, a4, a5 and up to infinity, we will get a0 plus a1x plus 1 by 6 into a0 minus a1 into x3. This is the value of a3. Okay, plus, and a4 is equal to, you know, 1 by 12 into a1 into x to the power 4, and a5 is equal to minus 3 by 40 into a0 minus a1 into x to the power 5, and up to infinity. Okay, so after simplifying this equation, we will get a0 into y is equal to a0 into 1 plus 1 by 6 into a3 minus 3 by 40 into a5 and up to infinity, plus a1 into x minus 1 by 6 into a3 plus 1 by 12 into x4 plus 3 by 40 into x to the power 5 and up to infinity. So where a0 and a1 are arbitrary constants. Okay. So this is the solution of the series solution of the given differential equation, and this series solution is in terms of a0 and a1. After that, we will discuss the second method of series solution of ordinary differential equation. The method, it will be method of Frobenius. Okay. So here is the example of the second method. Use method of Frobenius to find the solution of the differential equation x into x minus 1 y double dashed plus 3x minus 1 y dashed plus y is equal to 0. Okay, so here is the solution of the given differential equations. The given equation, it will be x into x minus 1 y double dashed plus 3x minus 1 y dashed plus y is equal to 0, and we can write it equation number 1. So now comparing this equation with p0 of x into y double dashed plus p1 of x into y dashed plus p2 of x into y is equal to 0. Okay, so where p0, p1, p2 are the polynomial function in x or constant, and here p0 of x is equal to x into x minus 1. So p0 of 0, so at the point x is equal to 0, it will be 0. So x is equal to 0 is the singular point of equation 1. So if the point x is equal to 0 is singular, then we cannot apply the general method for solving the differential equation. So in that case, we cannot apply the general method to solve the differential equations. Okay. So now you know p of x is equal to p1x by p0x, and q of x is equal to p2x by p0x. Okay, so where px is equal to 3x minus 1 by x into x minus 1, and q of x is equal to 1 by x into x minus 1. And x minus 0 into p of x, and it will be 3x minus 1 by x minus 1, and x minus 0 whole square into q of x is equal to x square into 1 by x into x minus 1, that is x by x minus 1. Therefore, x into p of x and x square into q of x process derivative of all orders in a neighborhood of x is equal to 0. Okay, so the first order derivative, second order, third order, okay, are all exist at x is equal to 0 or in a neighborhood of x is equal to 0. So hence x is equal to 0 is a regular singular point, not a ordinary point in that case. Okay. So consider the solution of equation 1 and in the form. So when x is equal to 0 is a regular singular point, then in that case the solution is of the form y is equal to summation over n is equal to 0 to infinity n into x to the power m plus n, where a0 is not equal to 0. And if the point x is equal to 0 is a regular point, then the form of the solution, it will be summation n is equal to 0 to infinity n into x to the power n. Okay. But in that case, the solution of equation 1 in the form y is equal to n is equal to 0 to infinity n into x to the power n plus n, where a0 is not equal to 0, and we can write it equation number 2. So therefore, the first derivative of y, it will be summation over n is equal to 0 to infinity m plus n into a n x to the power m plus n minus 1, and the second order differentiation, it will be summation n is equal to 0 to infinity m plus n into m plus n minus 1 n into x to the power m plus n minus 2. So now substituting these values in equation 1, that means y, y dash and y double dash in equation 1, will get this one. Okay, that means x into x minus 1 summation n is equal to 0 to infinity m plus n into m plus n minus 1 into n x to the power m plus n minus 2 plus 3x minus 1 into summation over n is equal to 0 to infinity m plus n x to the power m plus n minus 1. Okay, plus summation over n is equal to 0 to infinity n into x to the power m plus n is equal to 0. So after putting the value of y, y dash and y double dash, we will get this one. So after simplifying this equation, we will get summation n is equal to 0 to infinity m plus n into m plus n minus 1 n into x to the power m plus n. Okay, after multiplied by x square, we will get this one, minus 1 into this, that means minus summation over n is equal to 0 to infinity m plus n into m plus n minus 1 into n x to the power m plus n minus 1, okay, plus 3x into this, that means 3 into summation n is equal to 0 to infinity. So after multiple by x in that summation, we will get this one, this term, that means m plus n into x to the power m plus n into a minus summation n is equal to 0 to infinity, that means minus 1 into this m plus n into x to the power m plus n minus 1 plus last term, that means summation n is equal to 0 to infinity n into x to the power m plus n is equal to 0. The last term will remain same. So from this one, and from this series solution we will get summation n is equal to 0 to infinity m plus n into m plus n minus 1 plus 3 into m plus n plus 1 into n x to the power m plus n. So this is the coefficient of n into x to the power m plus n, and the second one, so this is the coefficient of n into x to the power m plus n minus 1. So from this equation we will get summation over n is equal to 1 to infinity m plus n minus 1 m plus n minus 2 plus 3 into m plus n minus 1 plus 1 into an minus 1 x to the power m plus n minus 1 minus the second term, it will remain same, okay, that means the second summation it will remain same, and the first summation will changed, and it will be n is equal to n minus 1, okay. So therefore the above series implies n is equal to 1 to infinity m plus n whole square minus 2 into, okay, after simplifying this we will get 2 into m plus n minus m plus n plus 2 plus 3 into m plus n minus 3 plus 1 into a n minus 1 x to the power m plus n minus 1, and the second one, this is actually the second series, okay. So from this we will get summation n is equal to 1 to infinity m plus n whole square a n minus 1 x to the power m plus n minus 1 minus m square into, okay, m square into a0 x to the power n minus 1 minus summation n is equal to 1 to infinity m plus n whole square n into x to the power m plus n minus 1 is equal to 0. So the above series is reduced to this, and this is equation number 3. So which is an identity in x equating to 0, the coefficient of the lowest power of x, namely x to the power m minus 1, and then from equation 3 we will get the identical equation minus m square a0 is equal to 0. So from this we will get m is equal to 0 comma 0, where a0 is not equal to 0. So next, equating to 0 to the coefficient of x to the power m plus n minus 1, and the recurrence relation is given by, and this is the recurrence relation, that means m plus n whole square a n minus 1 minus n is equal to 0, okay. So this is the coefficient of x to the power m plus n minus 1, and the coefficient of x to the power m plus n minus 1 will be the recurrence relation of the given differential equation, and it will be a n is equal to a n minus 1 for all n greater or equals to 1, and we can write it equation number 4. So therefore if we put n is equal to 1 2 3 4 and up to infinity in equation 4, we will get a1 is equal to a0, a2 is equal to a1 and a1 is equal to a0 again, a3 is equal to a2 and a2 is equal to a0, so a2 is equal to a0 again, a4 is equal to a3 and a3 is equal to a0, and so on, okay. That is a1 is equal to a0, a2 is equal to a0, a3 is equal to a0, and up to n is equal to a0. So now substituting these values of ai's in equation 2, and you know equation 2 is the general solution of the given differential equation, and it will be y is equal to a0 x to the power m plus a1 x to the power m plus 1 plus a2 into x to the power m plus 2 plus a3 into x to the power m plus 3, and up to infinity. This is the general solution of the given differential equation, where a0 is equal to a1 is equal to a3, okay, and so on. So therefore y is equal to a0 into x to the power m plus a0 into x to the power m plus 1 plus a0 into x to the power m plus 2, but a0 is is equal a1 is equal to a0, a2 is equal to a0, a3 is equal to a0, and so on. Now we'll take a0 into x to the power n as common from this series. We'll get a0 into x to the power m into 1 plus x square plus x to the power 3 and up to infinity. And this is the series of 1 minus x whole to the power minus 1. So y is equal to a0 into x to the power m into 1 minus x whole to the power minus 1. And therefore del m del y del m, and this is the partial differentiation with respect to m, it will be a0 into x to the power m 1 minus x to the power minus 1 into log x. Okay, so x to the power m, the derivative of x to the power m is equal to x to the power m into log x. So therefore the required complete solution of the given differential equation, and it will be y is equal to c1 y at m is equal to 0 plus c2 into del y del m at m is equal to 0. And y at m is equal to 0, it will be a0 into 1 minus x whole to the power minus 1, and del m del y at m is equal to 0, it will be a0 into 1 minus x whole to the power minus 1 log x. So after simplifying, it will give a plus b log x into 1 minus x to the power minus 1. Okay, so where a is equal to c1 a0 and b is equal to c2 a0 are the arbitrary constant. So this is the required solution of the given differential equation, where x is equal to 0 is the regular singular point. Okay, so after that we'll take one more example on the Fabina's method. So obtain the power series solution of the differential equation 5xy double dash plus 3y dash plus 2y is equal to 0. So comparing this equation with p0x into y double dash plus p1x into y dash plus p2x into y is equal to 0, where p0, p1, p2 are the polynomial function in x or constant. So we have p0 of x is equal to 5x. Okay, so comparing this equation with the given equation, you get p0 of x and it will be 5x. And at x is equal to 0, it will give 0. So x is equal to 0 is the regular singular point, not a ordinary point. So in an ordinary point where p0 of x is not equals to 0 at x is equal to a. Okay. So now p of x, and you know p of x is equal to p1x by p0x, and it will give 3 by 5x, and q of x is equal to p2x by p0x, and it will give 2 by 5x. Okay, so therefore x minus 0 into p of x, and it will give 3 by 5, and x minus 0 whole square into q of x, and it will give 2x by 5. So therefore x into px and x square into q of x process derivative of all orders in a neighborhood of x is equal to 0. So that is first order, second order, third order, fourth order. Okay, or all our derivatives are exist in a neighborhood of x is equal to 0. So x is equal to 0 is a regular singular point of equation 1. So in that case, we will take a solution of equation 1 in the form y is equal to summation n is equal to 0 to infinity n into x to the power n plus n. Okay, this is the solution of the given differential equation, where x is equal to 0 is the regular singular point. So in that case, we will apply the Fabina's method of the given differential equation. So y is equal to summation n is equal to 0 to infinity n into x to the power n plus n, where a0 is not equal to 0, and we can write it equation number 2. So now differentiate this solution, that means y is equal to this, we will get summation n is equal to 0 to infinity m plus n into n x to the power n plus n minus 1, and the second order differentiation, it will give n is equal to 0 to infinity m plus n into m plus n minus 1 an x to the power m plus n minus 2. Okay, so now substituting these values in equation 1, that means y dash and y double dash in equation 1, will get 5x into summation n is equal to 0 to infinity m plus n into m plus n minus 1 an x to the power m plus n minus 2. Okay, after putting the value of y double dash in equation 1, we get this one, plus 3 into y dash. So here in that case, where y dash is equal to this, so summation n is equal to 0 to infinity m plus n into x to the power m plus n minus 1, okay, plus 2 into y, that means n is equal to 0 to infinity n into x to the power n plus n is equal to 0. Okay, so So therefore, after multiple by x on that summation, we'll get 5 into summation n is equal to 0 to infinity m plus n minus 1 into n x to the power m plus n minus 1. Okay, this is the first term. And second term it will remain same. That means 3 into summation n is equal to 0 to infinity m plus n x to the power m plus n minus 1. And third term will remain same. That means 2 into summation n is equal to 0 to infinity n into x to the power m plus n, and it will be 0. Okay, and the above equation, it is reduced to 5m into m minus 1 a0 x to the power m minus 1 if we put n is equal to 0 in that equation. Okay, we will get this one, plus 5 into summation n is equal to 1 to infinity m plus n minus 1 n into x to the power m plus n minus 1, plus, if we put n is equal to 0 in that equation, we get 3m into a0 x to the power m minus 1 plus 3 into summation over n is equal to 1 to infinity m plus n an into x to the power m plus n minus 1. Okay, but the last term it will be 2 into summation n is equal to 1 to infinity. So in that case, n is equal to n minus 1. So that is n is equal to 1 to infinity a n minus 1. So okay, so n is replaced to n minus 1. That means n minus 1 into x to the power m plus n minus 1 is equal to 0. So therefore, the above equation is reduced to m into 5m minus 2 into a0 x to the power m minus 1 plus summation over n is equal to 1 to infinity. Okay, that means the second term, fourth term and fifth term. From these three terms we will get 5 into m plus n minus 1. Okay, plus 3 into m plus n plus 2 into a n minus 1 into x to the power m plus n minus 1 is equal to 0. Now this equation is implies 5 into 5m minus 2 into a0 x to the power m minus 1 is the first term, plus summation n is equal to 1 to infinity m plus n 5m plus 5n minus 2 into n plus 2 into a n minus 1 x to the power m plus n minus 1 is equal to 0, and we can write it equation number 3. And which is the identity in x, so equating to 0 the coefficient of the lowest power of x, that means x to the power m minus 1. Then equation 3 gives identity equation, that means 5m minus 2 into m into a0 is equal to 0. Okay, that means m is equal to 0 comma 2 by 5. So from this we will get the value of m, and it will be 0 and 2 by 5, but a0 is not equals to 0. And here the roots of the identity equation are unequal, so we do not differ by an integer. So next, equating to 0 the coefficient of x to the power m plus n minus 1, we get the recurrence relation as, so this is the recurrence relation when we put the coefficient of x to the power m plus n minus 1. So the coefficient of x to the power m plus n minus 1, it will be m plus n into 5n plus 5n minus 2 an plus 2 into an minus 1 is equal to 0 for all n greater equals to 1. So from this equation we will get the coefficient of n, and it will be minus 2 by m plus n into 5m plus 5n minus 2 into an minus 1 for all n greater equals to 1, and we can write it equation number 4. So this equation is called a recurrence relation of the given differential equation. And if we put n is equal to 1, 2, 3, 4 up to infinity, in equation 4 we get a1 is equal to minus 2 by m plus 1 into 5m plus 3 into a0. a2 is equal to this, that means minus 2a1 by m plus 2 into 5am plus 8, that means minus 4a0 into this. a3 is equal to this, that is 2a0 by m plus 3 into 5m plus 13, that means 8a0 by this. Okay, and so on. So now substituting these values of ai's in equation 2, and we will get y is equal to a0 into x to the power n into 1 minus 2x by m plus 1. This is the value of a1, that means 2x by m plus 1 into 5m plus 3 plus a2, that means 4x square by m plus 1, m plus 2, 5m plus 3, 5m plus 8. Okay, and so on. So these are series solutions of the given differential equation. So at m is equal to 0, we'll get the solution of y, and it will be a0 into 1 minus 2x by 3 plus x squared by 12 minus x cubed by 234 and up to infinity. Okay. And at m is equal to 2 by 5, and it will give a0 into x to the power 2 by 5 into 1 minus 2x by 7 plus x squared by 42 minus x cubed by 1071 and up to infinity. Okay. So for the different value of m, we'll get the two different series solution. That means a0 into this and a0 into this. That means a0 into x to the power 2 by 5 into 1 minus 2x by 7 plus x squared by 42 and up to infinity. Okay. So hence the required complete solutions is y is equal to c1 into y at x is equal m is equal to 0 plus c2 into y at m is equal to 2 by 5, and it will give a into 1 minus 2x by c3 plus x square by 12 minus x cube by 234 plus infinity up to infinity. This is the value of y at m is equal to 0, and this is the value of y at m is equal to 2 by 5, and it will be 5 into 1 minus 2x by 7 plus x square by 42 minus x cube by 1071 and up to infinity. So where a is equal to c1 a0 and b is equal to c2 a0, and these are the arbitrary constant. Okay, so this is the required series solutions of the given differential equation, where x is equal to 0 is the regular singular point. So I'll stop here. Thank you.